Swayam Prabha. Digital India. Educated India.
Hello students, today we are actually reached the end of this particular course. So at the same time, I am feeling very glad that we could really discuss a very important topic for today. But at the same time, we are finishing something, so definitely. But I hope this particular course you will continue to take in your own experience and also whatever different professional work you do in that. So let us go for certain discussions that what basic things I was planning to deliver to you and what actually happened through the modules, and then we will conclude this. So the course was aimed for, it has been structured to establish urban systems as ecological systems governed by material and energy flows, feedback mechanism and biophysical limits. So probably that's not the lens always we remember to look when we look at the urban systems. The intent is to move urban analysis away from static land use descriptions toward a process-based systemic understanding of cities as coupled socio-ecological entities. Urban ecosystems are treated here as anthropogenically regulated systems where human decisions replace natural regulation, often leading to imbalance, threshold exceedance, and risk amplification. What the course has operationalized? Across the modules, the course has operationalized structural decomposition of urban ecosystems into biophysical, socioeconomic, institutional, and technological subsystem. And under institutional, we discussed a lot about the governance also. Process diagnosis of altered carbon, water, heat, and nutrient cycles and their interactions. Functional interpretation of imbalance, ecosystem services, resilience, and carrying capacity as system outcomes. And this has enabled a diagnostic reading of cities rather than form or sector based interpretation. Analytical and decision capacity developed. By the end of the course, learners have developed the ability, I believe, to apply ecosystem theories and limiting factor logic to urban context, to evaluate interventions based on functional performance rather than prescriptive norms, to distinguish between grey infrastructure, ecological engineering, and hybrid nature-based solutions, to use assessment tools as feedback mechanisms for adaptive planning and governance, because we are saying that always the system is now changing, it's uncertain. So adaptive planning is very crucial. This represents a shift from control-oriented and certainty-based planning to adaptive, evidence-informed urban ecosystem management. And we will be also going for the summary of certain modules which we could not complete till now. Module 1, 2 and 3 we have already covered. Summary for the module 4 I will cover now. Urban ecosystem and CO2 and methane was the first lecture under this module 4. Urban ecosystems act as carbon sources, disrupting natural cycles through linear metabolism and fossil fuel dependence. And we discussed the mechanism, imbalances. Methane we discussed separately other than the CO2. So, keywords of this lecture was carbon cycle, greenhouse gas, urban metabolism, carbon imbalance, vertical emissions, layering. In the next lecture, we discussed a very important phenomenon, that is urban heat. UHI effect, which makes cities significantly warmer than the rural surroundings due to modified land cover and geometry. The causes, we talked about the urban geometry, surface materials and the evapotranspiration change. Structure, urban canopy layer and the urban boundary layer. We have also discussed LCZ here. Cities are now being mapped using the local climate zones to identify heat hotspots based on build types and land cover. So the keywords are UHI, urban boundary layer, and urban canopy layer, local climate zones, sky view factor, etc. In the next lecture, we discuss the urban ecosystem imbalances and challenges. So we started with the concept of urban critical zone, which is dynamic interface where socio-economic drivers reshape ecological systems, often causing the imbalances. And the 6 dimensions we have discussed at length, that imbalances manifest across biophysical flows, ecological, the habitat, chemical, the pollution angle, socio-ecological, the equity, economic and temporal dimensions. And we discussed the ecological impact of them, chemical impact of these cities as chemical reactors. We took the cities as the chemical reactor and try to understand that where the pollutant accumulates and the environment's capacity. In lecture 19, urban ecosystem balance, the balance is not static but dynamic equilibrium where ecological processes and human functions mutually reinforce one another. The transition strategy, moving from fail-safe, rigid control to safe-to-fail, is essential for regaining balance. Socio-ecological balance ensures equitable access to ecosystem services through participatory and accountable governance. Biophysical balance achieved when the flows of energy, water, and nutrients operate within the regenerative limits of the local environment. Dynamic equilibrium, regenerative limits, socio-ecological balance, safe-to-fail, adaptive harmony. Carrying capacity is the maximum population or activity level an urban environment can sustain without irreversible degradation. Assessment model tools include the SAFE model, feedback evaluation and ecological footprint to measure pressure against biocapacity. We also discussed other models as well. Capacities range from biophysical and infrastructure to social and institutional. We discussed the case study of Agra, where SAFE and other models were used, and to identify that non-developable heritage buffers and water bodies severely limit the city's horizontal expansion. And in the module 5, the 5th week, we have discussed the integration of concepts and theories in urban ecosystem. The first lecture under that particular module was ecosystem concepts for urban integration. Key concept is natural ecological concepts are translated into urban planning tools to create resilient hybrid infra. Ecological niches we discussed in cities, this translates to designing specific spaces that support diverse life forms. Keystone species, which are the urban equivalents, include pollinators and community gardens that play a disproportionately important role in sustaining local biodiversity. Then we talked about their cases, application cases, biophysical as well as ecological. And the keywords for this lecture was ecological niche, keystone species, pond city, skyrise greenery and biotope area factor. In the next lecture, city and ecosystem theories were being discussed, integrating ecosystem theories from energy flow to homeostasis. That helps frame the cities as complex adaptive system. Thermodynamics, the maximum power principle suggests successful cities organized to maximize useful energy capture and transformation. Succession theory guides urban regeneration, viewing the city as an evolving landscape that recovers from disturbances. Law of the minimum identifies the scarcest resource that limits the entire system's resilience and growth. So, we discuss succession theory, homeostasis, maximum power principle and law of the minimum. In the next lecture, case studies, city and ecosystem theories, we discuss Curitiba, Rotterdam, Los Angeles, Bangalore, and these cases were actually bringing out reparative justice, water management, adaptive cycle, these keywords. In the following lecture, Urban Ecosystem and Biodiversity, we discussed urban nature is distinct from urban biodiversity. Urban nature ranges from remnant pristine landscapes to novel wild ecosystems on abandoned sites. You can measure them. Biodiversity is assessed via species richness, abundance, and the balance of native versus invasive species. The paradox we discussed that cities can be biodiversity hotspots due to high habitat heterogeneity, but also centers of fragmentation and invasive species proliferation. And we know this fragmentation actually is a great challenge for ecological system to thrive. Urban nature, urban biodiversity, remnant landscapes, novel ecosystems, species richness, these were some of the keywords for this lecture. And the final lecture for this particular module was the IPCC and Biodiversity Conventions. Environmental governance evolved from the local brown agenda, that is pollution, sanitation, waste, to the global green agenda, conservation, climate. That is the focus. The catalyst was the Industrial Revolution, IPCC formation in 1988 by WMO and UNEP to provide the policy neutral scientific assessment of climate change. Key reports we discussed the Village Conference of Austria and Scope 29, which laid the scientific foundation for the IPCC and subsequent climate conventions. Module 6 and 7 we have discussed already in lecture 58, and module 8 also we discussed the summary in lecture 59. Now let us see the module 9, nature based solutions. Only a few weeks back we have discussed it, so you remember them, I know. BGI, key concept we discussed, PCM matrix model, rain gardens, biosoils. We have gone for certain details also, technical details. Rain gardens and biosoils, permeable pavements and urban forests. BGI, PCM, rain gardens, biosoils, permeable pavements were the discussion under this particular first lecture of module 9. Environmental engineering focuses on end-of-pipe treatment using physical, chemical and biological principles to meet regulatory standards. And for this environmental engineering discussion, we brought the focus areas of wastewater treatment, solid waste management and soil remediation. And in each cases, not only we discuss the theoretical precincts, we also has gone for the how to do it and case studies. So, environmental engineering, wastewater treatment, biofiltration, phytoremediation, waste stabilization ponds were the key words for the lecture 42. Next lecture was on ecological engineering, which designs self-sustaining systems that integrates human society with the natural environment using solar energy. Unlike environmental energy's control approach, ecological engineering partners with nature through self-design, where the system selects species mix adapted to the conditions. Bioretention cells and constructed wetlands, Miyawaki methods we discussed, and we also tried to understand pros and cons of this method. So, the keywords were ecological engineering, self-design, constructed wetland, bioretention, Miyawaki method. In the fourth lecture of this week was application potential for NBS. So, effective NBS requires converging BGI, spatial planning, environmental engineering for treatment mechanics and ecological processes from the ecological engineering. That was the key concept of this lecture. We discussed hybrid infrastructure, integrated NBS, and we talked about the implementation span, where the scales from the micro to macro and which requires the adaptive management and monitoring. So, not only having that initially, but also to maintain it. So, the keywords for this particular lecture was NBS convergence, hybrid infra, co-benefits, adaptive management, integrated systems. And the final lecture of that week was policy framework for nature-based solution, because ultimately we do understand it is very important to make sure that nature-based solutions are not only implemented but also been properly managed and augmented, scaled up. So, mainstreaming NBS requires adaptive governance, shifting from rigid master planning to collaborative cross-scale management. We talked about IUCN global standard and India's policy architecture. We talked about smart city missions and Amrut. Financial frameworks also we discussed, because that is very important for any NBS solution to be successful. Keywords for this lecture was adaptive governance, IUCN global standard, smart city mission, green bond, policy framework. And we will come for the 10th module now, which is assessment of urban ecosystem. First lecture was challenges in designing and deploying NBS. Key concept we discussed, that implementation gap. Governance silos, brought back that into our discussion, regulatory rigidities and maladaptation risk. These were the discussion. With the cases, we discussed them. Next lecture was urban ecosystem assessment, and in that we talked about SES and SCTS again, biophysical tools like remote sense and landscape metrics, vulnerability mapping and governance capacity. These were the major discussion points. In lecture 48, the biodiversity ecological footprint, this was discussed in details, how to really, what it is, the ecological footprint, and how that framework has brought into different parameters to understand the biocapacity and regenerative capacity. We discussed the handprint as well, complementary metric quantifying positive actions to balance the negative footprint. Ecological footprint generally gives us the notion of the negative footprint. City biodiversity index followed, and where we have discussed the framework, and we have also discussed few examples that how to really use this particular index. In many Indian cities, we can see gradually city biodiversity index is being used as a base case and then to monitor the improvement. And last lecture of this particular week was urban infrastructure assessment. So, we discussed about urban ecology, which treats infrastructure as an active agent that modifies ecological flows, shifting from grey only to hybrid performance. And we talked about the linear intrusion, performance-based planning and the resilience dividend in this particular important lecture. Performance-based planning is again a very important paradigm shift which moves from prescriptive standards to outcome metrics like landscape permeability and flood resilience. Summary for last two modules, future of urban ecosystem. SETI we discussed in lecture 51, science, engineering, technology and innovation. In lecture 52, ecology and future cities. And I am not going into details because just few days back we have finished this. Lecture 53, instrumented studies. Lecture 54 was on case studies on eco-engineering. And the final discussion with which we completed the 11th week, that was best management practice on eco-engineering solutions for water. And the 12th module this week, we started with the risk and BGI potential assessment tool, followed by case study on BGI solutions. And then we discussed a very important framework, that is geosemantic framework, which can help you in identifying the hotspot from the stress side, and also you can take a decision where to intervene. And this is based on the advanced tools and technologies like GIS, remote sense mapping and also statistical tools. Demonstration of geosemantic, that I have shown you that how we have done this application of geosemantic. I should not forget to remind you that this tool was developed, this framework was developed in the climatology lab of IIT Roorkee, and we had utilized it for the city of Guwahati for water. So now let us conclude this particular lecture as well as the entire course with lot of expectations, like planning interventions influence urban ecosystems indirectly through their effects on flows, feedbacks and limiting factors, and I hope by now you have understood that. Understanding these mechanisms is essential for informed and adaptive urban decision making, and I am really hopeful that you will be really the people who will be doing this urban decision making. Urban ecosystems are best understood through their behavior rather than their form. Accordingly, this course has focused on developing the analytical capacity to interpret system behavior rather than promoting isolated tools or solutions. The enduring value of the course lies in a system-based ability to diagnose the urban ecological conditions, interpret risk and resilience, and support adaptive decision making as cities continue to evolve. With this, I thank you. We have finally reached the end of this course. I hope you enjoyed the course and you will be really implementing. It's an application oriented, thought provoking course we have designed. And for this course, let me thank my research scholars who have been part and parcel of this entire course journey, Ms. Sakshi Goel and Mr. Architect Planner Kshitij Agarwal. Thank you.